Only seconds after the ground begins to shake, one apartment building starts collapsing floor by floor. Just a few meters away, another building of the same height sways gently but remains standing. Both structures experience the exact same earthquake, yet their outcomes are completely different. At first glance, it seems as though everything depends on how powerful the earthquake is. In reality, however, a building's survival is often determined by hidden engineering details that can't be seen from the outside.
Most people assume that the bigger, heavier, and stronger a building appears, the greater its chances of surviving an earthquake. But the truth is far more complex. It's not only about the amount of concrete or steel used, it's about how the entire structure responds to the Earth's vibrations. Today, we'll uncover why a single earthquake can wipe out an entire neighborhood while leaving nearby buildings almost untouched. Standing on solid ground, it's easy to believe the earth beneath your feet is perfectly stable. But hidden below the surface lies an immense reservoir of energy capable of tearing apart reinforced concrete as if it were paper.
Modern cities are built primarily with reinforced concrete. This material is exceptionally strong when compressed from above, allowing it to support the enormous weight of multi-story buildings. But its behavior changes dramatically when it's forced to bend or stretch. During an earthquake, reinforced concrete becomes far more vulnerable to tension than compression. The process begins deep underground when a fault suddenly ruptures. Fast-moving primary waves, known as P waves, race through the Earth's crust at incredible speed. These waves strike a building's foundation from below, causing the entire structure to jolt upward. Because concrete is designed to resist compression, it usually handles this initial vertical impact surprisingly well. But only moments later, a far more dangerous force arrives. Secondary waves, or S waves, move more slowly, yet they are responsible for much of the destruction. Instead of pushing upward, they shake the ground violently from side to side, creating powerful horizontal forces. This is where reinforced concrete faces its greatest weakness. As the foundation is suddenly pulled sideways, the heavy upper floors naturally resist the movement because of inertia. The base shifts first, while the top of the building tries to remain in place. The supporting columns begin to bend under enormous stress. If the columns lack enough flexible steel reinforcement, the surrounding concrete quickly develops deep cracks. Large sections of concrete break away, exposing the steel framework inside. Once those critical supports fail, the building rapidly loses its ability to carry its own weight. On the morning of September 19, 1985, this engineering failure became a tragic reality for the people of Mexico City. At 7:17 a.m., powerful seismic waves reached the capital, while millions of residents were still waking up. Without warning, the ground beneath the city began rising and falling by as much as 40 centimeters, creating motions that resembled massive ocean swells.
The city's rigid concrete buildings were never designed to withstand such violent horizontal movement. As the shaking intensified, cracking sounds echoed through the streets like artillery fire. Within minutes, the stress inside critical structural joints exceeded their physical limits. Steel reinforcement stretched beyond its capacity. Concrete crumbled into fragments, breaking its bond with the steel hidden inside.
One after another, buildings began collapsing under their own enormous weight. Entire neighborhoods that had once symbolized prosperity were transformed into fields of shattered concrete, twisted steel, and debris. Yet the most terrifying part of that disaster wasn't simply the strength of the earthquake. It was the fact that different buildings responded completely differently to the very same seismic waves. One of the greatest paradoxes of earthquake engineering is that the ideal height and exceptional strength of a building can sometimes become the very reason it fails.
Every physical object in the universe, whether it's a guitar string, a crystal glass, or a towering skyscraper, has its own natural vibration frequency. When the frequency of earthquake waves matches the natural frequency of a building, a dangerous phenomenon called seismic resonance occurs. Imagine pushing a child on a swing. If you push at random moments, the swing moves unpredictably and gradually slows down. But if every push is perfectly timed with the swing's natural rhythm, each movement becomes larger than the last. The same principle applies during an earthquake. Instead of slowing down, the building receives repeated pushes that match its natural motion, causing the oscillations to grow stronger and stronger until the structure reaches its breaking point. The devastating events in Mexico City in 1985 remain one of the clearest demonstrations of seismic resonance in action. The city itself was built on the soft clay bed of the ancient Lake Texcoco. Instead of absorbing seismic energy, this unstable ground acted like a giant amplifier. It transformed fast, irregular earthquake waves into slow, rhythmic oscillations with a period of almost exactly 2 seconds. That single characteristic proved disastrous. Short one-story buildings escaped with relatively little damage, and skyscrapers taller than 30 stories also remained largely intact. Their natural vibration frequencies simply didn't match the rhythm of the earthquake, allowing the seismic waves to pass through without creating dangerous resonance. Buildings between 6 and 15 stories, however, were far less fortunate. Their natural swaying period happened to be almost identical to the 2-second rhythm produced by the ground beneath the city. Every new shock arrived at exactly the right moment to increase the motion even further. Instead of slowing down, the buildings rocked more violently with each passing wave. Apartment complexes, hospitals, and office buildings, many of which had been constructed according to the engineering standards of the time, continued bending farther and farther until their supporting columns exceeded their structural limits. Once those columns failed, entire buildings collapsed under their own weight. This disaster revealed a surprising truth. Simply making buildings taller, thicker, or stronger wasn't always the answer. In certain situations, adding more concrete could actually increase the destructive effects of resonance instead of preventing them. Engineers realized they needed an entirely different strategy. Instead of forcing buildings to fight against the moving ground, why not separate the building from the earthquake itself? That revolutionary idea became known as base isolation. When a building is rigidly attached to the ground, nearly all of the earthquake's energy travels directly into the structure. To prevent this transfer of energy, engineers designed systems that allow massive buildings to move independently from the shaking earth below. For centuries, builders believed that the strongest foundation was one anchored as deeply and firmly as possible. Heavy piles were driven deep into the ground, so buildings would remain completely fixed. But during a powerful earthquake, that rigidity becomes a weakness. As the ground shifts violently, the foundation follows every movement instantly, forcing the entire building to absorb enormous stresses. Base isolation breaks this dangerous connection. Instead of resting directly on the foundation, the structure sits on specially engineered isolation bearings that function much like the suspension system of a high-performance vehicle. Each bearing is made from alternating layers of flexible rubber and thick steel plates. At the center of every isolator sits a solid lead core. Once those columns failed, entire buildings collapsed under their own weight. This disaster revealed a surprising truth. Simply making buildings taller, thicker, or stronger wasn't always the answer. In certain situations, adding more concrete could actually increase the destructive effects of resonance instead of preventing them. Engineers realized they needed an entirely different strategy. Instead of forcing buildings to fight against the moving ground, why not separate the building from the earthquake itself? Under intense deformation, the lead absorbs enormous amounts of energy by converting destructive motion into harmless heat, dramatically reducing the forces transmitted into the building itself. One of the world's most remarkable examples of this technology can be found beneath San Francisco City Hall.
After the 1989 Loma Prieta earthquake caused severe structural damage to the historic building, engineers chose not to simply repair the cracks. Instead, they carried out one of the most ambitious retrofitting projects ever attempted. The entire building, weighing tens of thousands of tons, was carefully lifted off its original foundation. Its supporting columns were cut away, and 530 lead-rubber isolation bearings were installed beneath the structure. Today, even if the nearby San Andreas Fault produces another major earthquake, the ground beneath City Hall can shift by nearly 70 centimeters in any direction. While the earth moves violently below, the massive building gently sways on its flexible supports, allowing it to remain stable and structurally intact. Yet protecting the foundation is only part of the challenge. As buildings grow taller, another powerful force begins to dominate: inertia. Even the most advanced foundation system cannot save a skyscraper if the structure above lacks the stiffness needed to resist twisting and bending. Modern architecture often favors wide-open spaces. Retail developers prefer ground floors with large glass storefronts instead of solid structural walls, while residential buildings frequently include open parking garages beneath the occupied floors. Although these layouts are practical and attractive, they can introduce one of the most dangerous weaknesses in earthquake engineering, a problem known as the soft story effect. To understand the soft story effect, imagine a simple cardboard box. As long as all four sides remain intact, the box can support a surprising amount of weight. But cut away one of its walls, and even a small amount of pressure causes it to collapse diagonally. Buildings can fail in much the same way. The upper floors are typically filled with apartments, walls, and interior partitions, creating a rigid, heavy block that may weigh thousands of tons. That enormous mass often rests on a much weaker ground floor, where solid walls have been replaced by slender columns or wide-open parking spaces. When an earthquake shakes the building sideways, the stiff upper floors move almost as a single unit, acting like a massive hammer. The thin supports below simply aren't strong enough to resist the intense horizontal forces. As those columns begin to bend or shear, the entire structure can collapse within seconds. A tragic example occurred on January 17, 1994, when the Northridge earthquake struck California's San Fernando Valley. One of the most devastating failures involved the Northridge Meadows apartment complex. The upper stories were built as conventional residential floors with strong walls and partitions. The ground level, however, was almost entirely an open parking garage supported by wood and steel columns. When violent horizontal shaking began, those supports were subjected to forces they were never designed to withstand. The columns buckled in one direction, and the rigid upper floors dropped almost instantly. The entire building pancaked onto its own first level, crushing it flat. 16 residents lost their lives, trapped beneath the structure they had called home. After disasters like this, engineers recognized that skyscrapers needed another line of defense. The challenge wasn't only protecting the foundation, it was controlling the tremendous momentum generated by the building itself. The taller a structure becomes, the greater the effects of inertia. When the base of a high-rise suddenly shifts during an earthquake, the upper floors naturally lag behind because of their enormous mass. Then, as the foundation changes direction, the top of the building continues moving due to inertia, swinging the opposite way with even greater force. If this motion continues unchecked, the upper floors can sway several meters from side to side. The resulting stresses place enormous strain on steel joints and structural connections, potentially causing catastrophic failure. To solve this problem, engineers introduced an ingenious technology known as the tuned mass damper. Its principle is surprisingly similar to the balancing pole used by a tightrope walker. When the performer begins to lean to one side, the heavy pole shifts the center of gravity in the opposite direction, helping restore balance.
Inside many modern skyscrapers, a massive suspended weight performs exactly the same function. Near the top of the building hangs an enormous steel sphere or block suspended by heavy cables. As the building begins to lean during an earthquake, the damper initially remains nearly stationary because of its own inertia. Moments later, it swings in the opposite direction, counteracting the building's motion. This opposing movement pulls the structure back toward its upright position while absorbing a significant portion of the earthquake's energy. Hydraulic dampers connected to the suspended mass then dissipate that energy, slowing the motion and preventing dangerous oscillations from building up. On April 3, 2024, the world witnessed this remarkable technology in action. A magnitude 7.4 earthquake struck off the eastern coast of Taiwan. Standing more than 500 meters above Taipei is the famous Taipei 101 skyscraper. Suspended between the 87th and 92nd floors is a giant golden sphere weighing approximately 660 tons. As powerful shaking spread across the city, cameras inside the tower captured the enormous pendulum swinging gracefully through the air with an amplitude of more than 1 meter. Rather than allowing the skyscraper to sway uncontrollably, the tuned mass damper absorbed much of the vibration. Thanks to this extraordinary engineering system, Taipei 101 remained structurally unharmed despite the intensity of the earthquake. These sophisticated technologies have dramatically improved the safety of modern landmark buildings. But they also raise an important question. What happens when ordinary residential buildings are constructed with hidden shortcuts, poor workmanship, or lower quality materials? Unlike iconic skyscrapers equipped with advanced engineering systems, many everyday buildings depend entirely on the quality of their construction, and that can make all the difference when the ground begins to shake. One of the biggest reasons buildings fail during earthquakes isn't the earthquake itself, it's poor construction. The most dangerous mistake is creating structural joints that lack ductility or the ability to bend without breaking. In a properly engineered building, concrete and steel work together as a single system. Concrete is responsible for carrying heavy compressive loads, while the ribbed steel reinforcement embedded inside it resists stretching and prevents the structure from pulling apart. But this partnership only works when the correct materials are used. If smooth steel bars replace ribbed reinforcement, they cannot grip the surrounding concrete effectively. During intense shaking, the steel can slide inside the concrete instead of reinforcing it, causing columns to lose much of their strength. An even more serious problem involves the steel ties that wrap around the vertical reinforcement inside each column. These rectangular steel hoops are installed at regular intervals to hold the reinforcing bars together and confine the concrete under extreme pressure. Their purpose is critical. During an earthquake, they prevent the concrete from expanding outward and breaking apart, while allowing the column to flex without collapsing. When too few of these ties are installed, or when they are spaced too far apart, the column loses its ability to deform safely. Instead of bending and absorbing seismic energy, it snaps suddenly under heavy lateral loads. This hidden weakness became tragically clear on February 6, 2023, during the devastating earthquakes that struck southern Turkey. One of the disaster's most infamous collapses was the Renaissance residence complex in Antakya. The luxury development contained around 250 apartments and had been advertised as a modern, earthquake-resistant residential community. Yet when the ground began to shake, the 12-story building didn't merely develop cracks. The entire structure tipped over and collapsed onto its side. Subsequent investigations revealed serious construction deficiencies. The load-bearing columns contained far fewer steel confinement ties than engineering standards required, and the quality of the concrete itself failed to meet acceptable specifications. Without sufficient ductility, the lower structural joints were unable to flex and dissipate the tremendous forces generated by the earthquake. Instead, they fractured almost instantly. Once the base of the structure failed, the entire building lost its support, trapping hundreds of residents beneath the debris. Failures like these demonstrate why strict engineering standards are essential. But researchers are now looking beyond traditional construction methods toward materials capable of surviving earthquakes while returning to their original shape afterward. Even if a building remains standing after severe shaking, permanent deformation can leave it leaning so badly that demolition becomes unavoidable. Conventional steel often bends permanently once it has been subjected to extreme stress.